Subscribe to the channel so you don't miss out on any of these videos. Imagine a universe where the rules of reality, as we know them, simply don't apply. Where two particles, separated by light years of space, can instantly communicate with each other, as if distance didn't matter. That's not science fiction, it's a real phenomenon called quantum entanglement. Albert Einstein, one of the most brilliant minds in history, found it so baffling that he famously called it spooky action at a distance. But what does it mean? How can something that defies the very concept of space and time exist in our universe? And more importantly, what secrets could it hold about the true nature of reality? Quantum entanglement is one of the strangest mysteries in science, a puzzle so perplexing that it has left even the smartest physicists scratching their heads for nearly a century. Yet, as bizarre as it sounds, it's not just a theoretical idea. Experiments have proven time and again that entanglement is real. It's happening right now in the quantum fabric of the universe. And the implications of this phenomenon stretch far beyond science labs. They could revolutionize our understanding of everything from how the universe began to whether faster-than-light communication is possible. Let's dive into this mind-bending topic and uncover what quantum entanglement really is, how it works, and why it matters. But here's a warning: the deeper we go, the weirder things will get. Because to understand entanglement, you have to let go of some of the most basic assumptions you've always held about reality. So buckle up, this is going to be a journey into the heart of one of the universe's greatest mysteries. At its core, quantum entanglement starts with a very simple idea. Imagine two particles, like tiny building blocks of matter. In the world of quantum physics, these particles don't behave like the objects you see around you every day. Instead of being in one specific place or state, they exist in a kind of blur of possibilities. This is called a superposition, and it means a particle doesn't choose a definite state until it's measured. It's as if a coin is spinning in the air, both heads and tails at the same time, until someone catches it. Now, here's where things get really weird. When two particles become entangled, their states become linked. No matter how far apart they are, whether they're inches apart or on opposite sides of the galaxy, the state of one particle will instantly determine the state of the other. If you measure one particle and find it spinning up, the other will immediately be spinning down, even if no signal could have possibly traveled between them in time. It's like they share a secret connection that ignores the speed of light, the supposed cosmic speed limit. But how does this work? The truth is, nobody knows for sure. Scientists have theories, but quantum entanglement refuses to fit neatly into the rules of classical physics. Einstein himself struggled with the idea, arguing that it couldn't be complete. He believed there must be hidden variables, some unknown factors that we hadn't yet discovered, making the particles behave this way. However, experiments in the 20th century, particularly those conducted by physicist John Bell, showed that hidden variables couldn't explain what was happening. Entanglement is a real, undeniable phenomenon. One of the most mind-blowing aspects of quantum entanglement is its potential connection to non-locality. Non-locality is the idea that events occurring in one location can have instantaneous effects elsewhere, without anything physically traveling between them. This concept shatters our traditional understanding of cause and effect, where actions are limited by distance and time. In the quantum world, it seems that the fabric of space and time itself might be irrelevant. This raises some profound questions. Could the universe be fundamentally interconnected at a level we can't yet perceive? Some scientists think that entanglement hints at a deeper layer of reality, one where space and time are not the ultimate framework of existence but emerge from some more fundamental quantum structure. If that's true, then everything in the universe, from the smallest particle to the largest galaxy, might be linked in ways we're only beginning to imagine. Quantum entanglement also has some incredible potential applications. For example, in the field of quantum computing, entanglement is a key ingredient that could make these machines exponentially more powerful than today's computers. By using entangled particles to perform calculations, quantum computers can process information in ways that classical computers simply can't match. This could revolutionize everything from medicine to cryptography. And speaking of cryptography, entanglement could also pave the way for ultra-secure communication systems. Quantum encryption relies on the fact that any attempt to eavesdrop on an entangled system would immediately disrupt it, making it impossible to intercept messages without being detected. Imagine a future where your personal data is not just password protected but guarded by the laws of physics themselves. But perhaps the most tantalizing possibility is the idea of faster-than-light communication. While most scientists agree that entanglement can't be used to send messages directly, the phenomenon challenges our understanding of causality and information transfer. Could there be a loophole we haven't yet discovered? Could entanglement be the key to connecting distant parts of the universe in ways that make interstellar communication, and maybe even travel, a reality? The implications of quantum entanglement don't stop there. Some researchers have speculated that it could play a role in the fundamental workings of the universe itself. For instance, could the mysterious force of gravity be linked to quantum entanglement on a cosmic scale? Could the fabric of space-time be held together by these invisible connections? And what about black holes, those enigmatic objects where the rules of physics break down? Recent studies suggest that entanglement might be crucial to understanding what happens inside a black hole and how information is preserved in the universe. If you think this all sounds too strange to be true, you're not alone. Even physicists who work on quantum mechanics admit that it's one of the most counterintuitive areas of science. Yet, despite its strangeness, entanglement is backed by solid evidence. Experiments using ultra-sensitive detectors and state-of-the-art technology have repeatedly confirmed its existence, leaving no doubt that this spooky action is real. And yet, as much as we've learned, we're still just scratching the surface. Quantum entanglement is like a window into a hidden layer of reality, one that operates on principles we can barely begin to comprehend. It challenges our understanding of everything, from the nature of particles to the structure of the cosmos, and forces us to confront the possibility that the universe is far stranger than we ever imagined. Quantum entanglement doesn't just challenge our understanding of space and time, it flips the script on what we consider to be the very fabric of reality. To grasp how profound this is, think about this. Everything you interact with, from your phone to the ground beneath your feet, seems to obey certain physical laws. These laws are what make the universe predictable, measurable, and to an extent, understandable. But at the quantum level, those laws seem to dissolve into something far less concrete. Quantum entanglement reveals that our traditional ideas about distance, separateness, and even causality might just be illusions, a shadow of a much deeper, hidden reality. To truly understand the scale of what's happening here, it's essential to explore the bizarre experiments that proved entanglement exists. One of the most famous is called the Bell test experiment, named after physicist John Bell, who laid the theoretical groundwork for testing quantum entanglement. In these experiments, scientists create pairs of entangled particles and send them to two separate locations. Then, they measure specific properties of each particle, like their spin or polarization. What they find is astonishing. The results of these measurements are correlated in ways that defy classical explanation. Even when the particles are separated by vast distances, their behavior remains linked. Imagine flipping two coins on opposite sides of the Earth and finding that every time one lands heads, the other lands tails, without fail. The correlation is so precise and instantaneous that it seems impossible unless some kind of faster-than-light communication is occurring. But here's the catch: entanglement doesn't actually transmit information in the conventional sense. Instead, it reveals a deeper connection that transcends our current understanding of physics. The implications of these experiments are profound. They tell us that the universe is inherently non-local, meaning that events in one place can be intrinsically connected to events elsewhere, regardless of distance. This flies in the face of Einstein's theory of relativity, which holds that nothing, no information, no influence, can travel faster than the speed of light. But entanglement doesn't involve anything traveling. It's as if the two particles are part of a single, unified system, no matter how far apart they are. This idea, that the universe might be fundamentally interconnected, is both thrilling and deeply unsettling. One of the most fascinating areas of research related to quantum entanglement is its potential connection to the phenomenon of quantum teleportation. This isn't the kind of teleportation you see in sci-fi movies, where entire objects or people are instantly transported from one place to another. Instead, quantum teleportation involves the transfer of information between entangled particles. Here's how it works. By entangling three particles and using one as a kind of intermediary, scientists can transfer the quantum state of one particle to another, even if they're far apart. It's not the particle itself that moves, it's the information about its state. This has huge implications for the future of technology, particularly in the realm of quantum computing and communication. Imagine a world where data can be transmitted instantly across any distance, without the risk of being intercepted or corrupted. Quantum teleportation could make that possible. It could also play a role in building a global quantum internet, a network where information is stored and shared in entangled particles, creating a level of security and speed that's unimaginable with today's systems. But the deeper mystery is what quantum entanglement tells us about the universe itself. Some physicists believe that entanglement could be the key to unifying the two great pillars of modern physics: quantum mechanics, which governs the very small, and general relativity, which governs the very large. These two theories have been incredibly successful in their respective domains, but they don't play well together. General relativity breaks down at quantum scales, and quantum mechanics doesn't account for gravity. Entanglement, however, might offer a bridge between these seemingly incompatible frameworks. One tantalizing idea is that the fabric of spacetime itself could emerge from quantum entanglement. This theory, often associated with the concept of ER equals EPR, short for Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations, suggests that entangled particles might be connected by microscopic wormholes. These wormholes, also known as Einstein-Rosen bridges, could be the threads that weave spacetime together. If this is true, then entanglement isn't just a weird quirk of the quantum world, it's a fundamental feature of the universe. This brings us to the question of how entanglement fits into the larger mysteries of the cosmos. Could it help explain the origin of the universe itself? Some theories suggest that the Big Bang, the event that created everything we know, might have involved a state of perfect entanglement, where all the particles in the universe were interconnected. As the universe expanded, these connections could have been stretched and preserved, leaving a hidden web of entanglement that links everything to this day. Entanglement might also hold clues to the nature of dark matter and dark energy, the mysterious forces that make up most of the universe but remain poorly understood. Could these phenomena be manifestations of large-scale quantum entanglement? Some researchers think it's possible. If so, studying entanglement could unlock secrets about the cosmos that have eluded us for decades. And what about consciousness? This is one of the most speculative but intriguing areas of study related to quantum entanglement. Some scientists and philosophers have wondered whether the mind itself might operate on quantum principles. Could entanglement play a role in the way neurons in the brain communicate? Could it explain phenomena like intuition, creativity, or even the feeling of being connected to something greater than yourself? While these ideas are still in the realm of speculation, they highlight just how far-reaching the implications of entanglement could be. The more we learn about quantum entanglement, the clearer it becomes that we're standing on the edge of a vast, uncharted frontier. Every experiment, every discovery, brings us closer to understanding the true nature of reality. But it also raises new questions, pushing the boundaries of what we know and challenging us to think in ways we never have before. What if space and time are just illusions, emergent properties of a deeper, entangled reality? What if the universe isn't a collection of separate objects but a single, interconnected whole? These are the kinds of questions that quantum entanglement forces us to confront. And yet, for all its complexity and strangeness, entanglement also has a kind of beauty to it. It reminds us that the universe is full of surprises, that the answers to its deepest mysteries might lie in places we've never thought to look. It's a testament to the power of human curiosity and imagination, a reminder that the quest to understand the cosmos is far from over. As we continue to explore this phenomenon, it's clear that we're only scratching the surface of what it can teach us. Entanglement is a doorway to a new understanding of the universe, one that challenges our assumptions and expands our horizons. It's a reminder that, no matter how much we think we know, the cosmos always has more surprises in store. And this is just the beginning. As scientists conduct more experiments and refine their theories, we may discover even more mind-bending aspects of entanglement that we can't yet imagine. The journey to understand this spooky action at a distance is far from over, and it promises to reshape our understanding of reality in ways we're only beginning to grasp. This interconnected journey leads us into some of the most profound questions of all. What is the ultimate fabric of the universe? Could entanglement hint at a reality that transcends the physical? And if so, what might this deeper reality mean for humanity's understanding of existence? One hypothesis emerging from the study of quantum entanglement is that the universe may operate as a form of quantum network. In this framework, particles aren't merely connected but actively communicate through a vast web of relationships, forming the foundation for the exchange of information across the cosmos. If true, this would redefine our understanding of not just physics but also communication, intelligence, and the concept of life itself. This brings us to the tantalizing question: could quantum entanglement play a role in the consciousness debate? Some theorists propose that consciousness might not be a purely biological phenomenon. Instead, it could involve quantum processes, possibly influenced or mediated by entanglement. This idea, though speculative, opens up fascinating possibilities. Could our thoughts, emotions, or decisions be influenced by non-local interactions at the quantum level? Could human consciousness itself be part of a larger, universal network? While there's no direct evidence for these ideas yet, they are grounded in intriguing parallels. For example, the brain operates through networks of neurons that transmit signals instantaneously. These networks bear a superficial resemblance to the interconnected web suggested by entanglement. If entanglement governs information exchange at the quantum level, it's worth considering whether similar principles might apply at higher scales of complexity. Another area where entanglement might play a surprising role is in understanding dark energy and dark matter, two of the greatest mysteries in cosmology. Together, these unseen forces make up about 95% of the universe, yet we know almost nothing about them. Some researchers hypothesize that quantum entanglement could offer clues. For instance, could dark energy be a manifestation of entangled particles exerting influence across vast cosmic distances? Could dark matter arise from entangled states that interact with ordinary matter in ways we don't yet comprehend? These questions are difficult to test experimentally, but advances in technology might bring us closer to answers. Cutting-edge observatories, like the James Webb Space Telescope, are already providing unprecedented insights into the structure and origins of the universe. Future experiments might probe whether the large-scale behavior of galaxies and other celestial bodies is influenced by quantum phenomena like entanglement. One particularly ambitious idea is the search for a quantum theory of gravity, a theory that would unite quantum mechanics with Einstein's general relativity. While relativity governs the behavior of massive objects like planets and black holes, quantum mechanics explains the behavior of the smallest particles. Reconciling these two frameworks has been one of physics' greatest challenges. Entanglement might hold the key. For example, the concept of space-time itself could emerge from entanglement. Some physicists believe that the geometry of space-time, the fabric in which all events occur, might be a result of quantum entanglement. In this view, the universe isn't made of matter or energy alone but also of relationships, encoded through entangled states. This idea has been explored in theories like ADS/CFT correspondence, which suggests that the structure of space in higher dimensions is mathematically equivalent to quantum field theories in lower dimensions. If this is correct, then entanglement might not just be a feature of the universe, it might be its very foundation. The implications are staggering. It would mean that everything we see, touch, and experience is built from an underlying network of entangled relationships, weaving the cosmos together like an intricate, invisible tapestry. As groundbreaking as these ideas are, they also raise questions about the limits of human understanding. Can we ever fully grasp the nature of entanglement? Or is it destined to remain one of the universe's most profound mysteries? These questions push us beyond the boundaries of science into the realm of philosophy, where concepts like infinity, eternity, and the nature of existence take center stage. Philosophically, entanglement challenges the notion of individuality. If particles are fundamentally connected, What does that say about our place in the universe? Are we truly separate beings, or are we part of a greater whole? Take, for example, the idea that observation affects reality, a concept tied closely to entanglement. In quantum experiments, the act of measurement collapses a particle's wave function, determining its state. Some interpret this as evidence that consciousness itself plays a role in shaping the universe. If true, it would mean that reality isn't fixed but is constantly shaped by our perceptions and actions, a concept with profound implications for how we live our lives. From a scientific perspective, entanglement could also inspire new approaches to sustainability and energy. For instance, if entangled particles can transfer information instantly, could similar principles be harnessed to create more efficient energy systems? Could we one day develop technologies that tap into the quantum nature of the universe to solve global challenges? The possibilities are endless, but they come with significant challenges. Understanding and harnessing entanglement requires precise control over quantum systems, something that's incredibly difficult to achieve. Even the slightest interference can disrupt an entangled state, a phenomenon known as decoherence. Overcoming this hurdle is a major focus of current research, and success could unlock a new era of technological innovation. Yet, for all its complexity, entanglement also reminds us of the beauty and mystery of the cosmos. It's a phenomenon that defies our expectations and invites us to see the universe in a new light, not as a collection of isolated parts, but as a deeply interconnected whole. It challenges us to think beyond the limitations of classical physics and embrace the strange, wondrous possibilities of the quantum realm. As we continue to explore entanglement, one thing is clear: it's a doorway to a deeper understanding of the universe, one that transcends the boundaries of space, time, and imagination. Whether it's unlocking the secrets of the cosmos, revolutionizing technology, or reshaping our view of reality itself, entanglement holds the promise of discoveries that could change the course of human history. Consider the possibility that, on a quantum level, everything in the universe is interconnected. If entanglement is not just a rare phenomenon but a fundamental aspect of reality, then every particle in your body could, in theory, be linked to particles on the other side of the galaxy. This paints a picture of a universe in which all matter and energy are part of a single, unified system, a cosmic dance where every movement influences the whole. This perspective aligns with certain interpretations of quantum mechanics, such as David Bohm's theory of the implicate order. Bohm proposed that the universe operates on two levels: an explicit, observable order, the world we see, and an implicit, hidden order, a deeper reality where everything is interconnected. In this framework, entanglement might be a glimpse of the implicate order at work, revealing the interconnectedness that lies beneath the surface of our everyday experiences. While these ideas are captivating, they are also deeply challenging. They push us to rethink fundamental concepts like space, time, and identity. For centuries, we've operated under the assumption that the universe is made up of discrete objects that exist independently of one another. Entanglement challenges this view, suggesting that the boundaries we perceive are, in many cases, arbitrary or even illusory. This has profound implications for how we approach not just physics but also philosophy, ethics, and even politics. If everything is connected, how should we treat one another? How should we treat the planet? Entanglement invites us to see ourselves not as isolated individuals but as parts of a larger whole, bound together by invisible threads that transcend space and time. In addition to these philosophical considerations, entanglement is forcing us to rethink the very foundations of science itself. Traditionally, science has been built on the principle of locality, the idea that objects are only influenced by their immediate surroundings. Entanglement defies this principle, suggesting that particles can influence one another instantaneously, no matter how far apart they are. This non-locality is deeply unsettling because it seems to contradict the theory of relativity, which holds that nothing can travel faster than the speed of light. Physicists are still grappling with this apparent contradiction, but some believe that entanglement might be the key to unifying quantum mechanics and relativity. These two pillars of modern physics have long been at odds, with quantum mechanics describing the behavior of particles on the smallest scales and relativity describing the behavior of massive objects on cosmic scales. Entanglement could be the bridge that connects these two realms, offering a deeper understanding of the universe's underlying structure. One promising avenue of research is the idea that spacetime itself might emerge from quantum entanglement. This radical hypothesis suggests that the fabric of the universe is not a static backdrop but a dynamic, interconnected web of relationships. In this view, spacetime is not a fundamental entity but a byproduct of the quantum entanglement that links all particles. This concept is being explored through cutting-edge theories like ADS/CFT correspondence, which uses mathematical tools from string theory to describe how spacetime might arise from quantum systems. If these ideas are correct, they could revolutionize our understanding of reality. They could reveal that the universe is not a collection of separate objects moving through an empty void but a single, interconnected whole, where everything is woven together by the threads of entanglement. This perspective has profound implications not just for physics but for every aspect of human thought, from art and literature to ethics. Yet, as we explore these possibilities, we must also confront the limitations of our knowledge. Quantum entanglement is a deeply mysterious phenomenon, and many of its implications remain speculative. While experiments have confirmed its existence, we are still far from understanding how or why it works. This mystery is both humbling and inspiring, reminding us that the universe is far stranger and more complex than we can imagine. It also reminds us of the importance of curiosity and imagination. The study of entanglement is a testament to humanity's ability to ask bold questions and seek answers in the face of uncertainty. It shows that, even in a world filled with challenges and uncertainties, there is still room for wonder, discovery, and the pursuit of knowledge. As we look to the future, the study of quantum entanglement will likely continue to reshape our understanding of the universe. It will raise new questions, challenge old assumptions, and open up new frontiers of exploration. And in doing so, it will remind us of our shared humanity, our deep connection to the cosmos, and our endless capacity for wonder. The journey into the mysteries of quantum entanglement is far from over. It is a journey that invites us to look beyond the surface, to question the boundaries we take for granted, and to embrace the interconnectedness that lies at the heart of existence. It is a journey that challenges us to think bigger, dream bolder, and imagine a universe where anything is possible. Quantum entanglement challenges us to explore not only the physical universe but also the nature of knowledge itself. What does it mean to truly understand something that seems so fundamentally counterintuitive? How can we grasp a concept that defies the very fabric of our intuitive understanding of space, time, and causality? This is where the role of mathematics becomes paramount. Mathematics often serves as the bridge between human intuition and the hidden truths of the universe. It is through mathematical formalism that we've been able to predict and test the existence of phenomena like entanglement. Schrödinger's equations, Bell's inequalities, and the experimental data from tools like photon pairs and quantum systems have all provided tangible proof of entanglement's reality. Yet, the equations themselves are only part of the story. They describe what happens, but not why it happens. Consider the EPR paradox, which Einstein, Podolsky, and Rosen proposed in 1935. They used this thought experiment to argue that quantum mechanics must be incomplete because it allowed for what Einstein famously called spooky action at a distance. The paradox forced physicists to confront uncomfortable questions about the nature of reality, questions that remain unresolved to this day. While experimental evidence has since confirmed that quantum entanglement is real and violates local realism, it has done little to explain the underlying mechanism. This brings us to a profound question: is reality deterministic or probabilistic? Classical physics operates on determinism, the idea that every event is caused by preceding events in a predictable way. Quantum mechanics, on the other hand, is inherently probabilistic. The state of a particle is described by a wave function, which provides probabilities for different outcomes rather than certainties. When two entangled particles are measured, their states seem to collapse instantaneously, as if they are communicating. But this communication defies classical logic. How does one particle know what measurement was performed on its partner, and why does its state adjust accordingly? Quantum entanglement's ability to connect particles instantaneously across space makes us question the most basic assumptions about separateness in the universe. This idea leads to philosophical and scientific debates about the nature of reality itself. If particles can influence each other regardless of the distance, does that mean the universe is more interconnected than we realize? Could everything at its core be part of a single, unified system? These questions challenge our classical worldview, where objects exist independently, bound by the constraints of space and time. Entanglement hints that our perception of separateness might be just that, a perception, not a fundamental truth. If entanglement represents a hidden unity, it forces us to rethink everything from the nature of individuality to the structure of the cosmos. One particularly compelling idea comes from the study of holographic principles. This theory suggests that the entire universe might function like a hologram, where every part contains the whole. In this framework, quantum entanglement could be the mechanism that encodes this interconnectedness. For instance, just as a holographic image holds all its information in every fragment, entangled particles could represent fragments of a deeper, unified reality. This theory has gained traction as researchers explore how black holes, with their enigmatic event horizons, might also operate holographically. The implications of this are staggering. If entanglement is the foundation of this holographic nature, it could mean that our universe is fundamentally a network of information. This aligns with another groundbreaking idea, that reality itself might be digital at its core. In this view, entanglement is akin to a cosmic program, stitching the universe together with rules that transcend our current understanding. But the philosophical implications don't stop there. Consider the concept of non-locality, which is the idea that events can influence one another without any physical connection or intermediary. Non-locality is a cornerstone of quantum mechanics, and entanglement is its most vivid demonstration. This phenomenon calls into question the very notion of causality, the idea that one event causes another in a linear fashion. In a non-local universe, causality might not follow the straightforward cause and effect chain we're used to. This challenges even Einstein's objections to entanglement. He famously called it spooky action at a distance, because it seemed to violate relativity's principle that nothing can travel faster than light. But non-locality doesn't imply faster than light travel. It implies that the particles aren't separate entities to begin with. They are, in essence, two parts of the same whole. It's as if the universe doesn't care about the distance between them, because, in some deeper sense, there is no distance. This brings us to one of the most provocative questions entanglement raises. Could non-locality explain some of the great mysteries of the universe? For example, what if the large-scale structure of the cosmos, the distribution of galaxies, stars, and planets, arises from quantum entanglement at the smallest scales? Some physicists hypothesize that the cosmic web, the vast network of filaments that connect galaxies across the universe, might be a macroscopic reflection of quantum entanglement. Another mystery that entanglement might illuminate is the strange phenomenon of time itself. Time, as we experience it, seems to flow in one direction, from the past to the future. But at the quantum level, the arrow of time becomes much less clear. Entangled particles, in particular, seem to operate outside our conventional understanding of time. Their correlations don't depend on when the measurements are made, only that they are made. This has led some researchers to speculate that time, like space, might be an emergent property rather than a fundamental one. If this is true, it could explain why entanglement works the way it does. In an entangled universe, the past, present, and future might all exist simultaneously, connected by a web of non-local interactions. This idea isn't just a theoretical curiosity. It could have practical applications in fields like quantum computing, where manipulating entanglement might allow us to cheat time in specific, controlled ways. Speaking of applications, one of the most exciting aspects of quantum entanglement is its potential for technological innovation. As mentioned earlier, quantum teleportation is already a reality in laboratory settings. While we're far from teleporting physical objects, the ability to transfer quantum states across distances has profound implications for communication. Imagine a future where information can be sent instantly and securely, immune to eavesdropping or interference. This could revolutionize industries ranging from finance to national security. Another potential application is in quantum cryptography, which uses the principles of entanglement to create unbreakable encryption. In a quantum system, any attempt to intercept a message disrupts the entanglement and reveals the intrusion. This kind of technology could create a new era of secure communication, safeguarding everything from personal data to global infrastructure. But perhaps the most tantalizing application lies in the realm of quantum computing. Unlike classical computers, which process information in binary bits, zeros and ones, quantum computers use qubits, which can exist in multiple states simultaneously thanks to entanglement. This allows quantum computers to perform complex calculations at speeds that would be impossible for even the most powerful supercomputers today. From simulating molecular interactions for discovery to solving optimization problems in logistics, quantum computing could transform countless fields. Yet, for all its potential, entanglement also raises profound ethical and philosophical questions. If the universe is fundamentally interconnected, what does that mean for our understanding of free will? Are our choices truly independent, or are they influenced by hidden, entangled factors we can't perceive? And if everything is connected, do we bear some responsibility for the state of the cosmos as a whole? These questions might not have easy answers, but they highlight the deep, existential implications of entanglement. And perhaps that's the most exciting part. Quantum entanglement isn't just a phenomenon to study, it's a reminder that the universe is full of surprises, waiting to be uncovered. In the vast, interconnected web of existence, there are mysteries we can't yet fathom, connections we can't yet see, and truths that will continue to inspire and amaze us for generations to come. The study of quantum entanglement opens up so many possibilities, and with each discovery, it seems as though we are peeling back yet another layer of the universe's infinite complexity. One of the most exciting aspects of entanglement is its potential to reshape our understanding of time and causality. Traditionally, we think of time as a linear progression, moving from the past through the present and into the future. But entanglement challenges this straightforward view. In an entangled system, the influence of one particle on another appears to happen instantaneously, regardless of the distance between them. This phenomenon suggests that our conventional notions of cause and effect might not hold at the quantum level. What if time itself is an emergent property, arising from the underlying entangled relationships that govern the universe? Some physicists propose that entanglement could be the key to understanding the true nature of time, perhaps even revealing that time as we know it doesn't exist at all. These ideas tie into broader concepts in physics, such as the block universe theory, which suggests that past, present, and future all exist simultaneously as part of a four-dimensional space-time structure. In this framework, entanglement might serve as a bridge, connecting events across time and space in ways we don't yet fully understand. This could have profound implications for our understanding of free will, determinism, and the nature of reality itself. Moving from theoretical physics to practical applications, quantum entanglement is also playing a crucial role in the development of quantum computing. Unlike classical computers, which process information in binary states, zeros and ones, quantum computers use quantum bits, or qubits, which can exist in superpositions of states. Entanglement allows qubits to work together in highly efficient ways, enabling quantum computers to solve problems that would be practically impossible for classical systems. This technology is still in its infancy, but its potential is staggering. Quantum computers could revolutionize fields like cryptography, discovery, artificial intelligence, and climate modeling. They could even simulate complex quantum systems, helping us to better understand entanglement itself. Yet, as with any powerful technology, quantum computing raises ethical questions. How will this technology be used, and who will control it? Could it exacerbate existing inequalities, or will it be a force for good, helping humanity address its greatest challenges? Another fascinating application of entanglement is in the field of quantum teleportation. While this doesn't involve physically transporting matter from one place to another, as in science fiction, it does allow for the transfer of quantum states between particles over large distances. This process relies on entanglement to transmit information instantaneously, and it has already been demonstrated in laboratory settings. While practical teleportation of objects or humans remains far beyond our reach, these experiments offer a glimpse into a future where information transfer could become nearly instantaneous, with profound implications for communication and data security. Entanglement might also play a role in solving one of the biggest puzzles in modern physics: the nature of black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They challenge our understanding of physics, particularly when it comes to the information paradox, the question of what happens to information that falls into a black hole. Some researchers believe that entanglement could offer a solution. One idea is that information isn't lost in a black hole but is instead preserved through entangled states. In this view, the event horizon of a black hole, the boundary beyond which nothing can escape, might act as a kind of hologram, encoding information about everything that falls into it. This concept, known as the holographic principle, suggests that the universe itself might be a vast, multidimensional hologram, with entanglement serving as the mechanism that ties everything together. These ideas are deeply speculative but also deeply exciting. They hint at a universe far stranger and more interconnected than we can currently comprehend. And they remind us that, despite all our technological and scientific progress, we are still in the early stages of understanding the cosmos. The implications of quantum entanglement extend beyond science and technology, touching on fundamental questions about the human experience. For instance, entanglement could offer new insights into the nature of relationships and connection. At its core, entanglement is about the idea that two entities can be profoundly linked, no matter how far apart they are. This concept resonates with human experiences of love, empathy, and connection, suggesting that the boundaries we perceive between ourselves and others might not be as solid as they seem. Even as we explore these profound ideas, it's important to remain grounded in the evidence. Quantum entanglement is a real, measurable phenomenon, but many of its implications remain speculative. As we continue to investigate, we must be careful to distinguish between what we know and what we hypothesize. This balance between curiosity and skepticism is what drives science forward, pushing the boundaries of knowledge while keeping us anchored to reality. At the same time, the mystery of entanglement reminds us of the importance of humility. The universe is vast and complex, and our understanding of it is still in its infancy. Every new discovery raises new questions, reminding us that the pursuit of knowledge is an ongoing journey, not a destination. And perhaps that's the true beauty of quantum entanglement. It's not just a scientific phenomenon but a doorway to wonder, inviting us to explore the unknown and expand our understanding of what is possible. As we continue to unravel the mysteries of quantum entanglement, we are not only learning about the universe but also about ourselves. We are discovering that the cosmos is more interconnected, more dynamic, and more mysterious than we ever imagined. And in doing so, we are reminded that we, too, are part of this vast, entangled web of existence, a web that spans not just the stars but the very fabric of reality itself. The implications of quantum entanglement stretch far beyond the physical realm, challenging deeply held assumptions about individuality and isolation. If particles can remain connected across vast distances, it raises the question: are any of us truly separate from the universe? Entanglement suggests that the idea of self, as an isolated entity, might be an illusion, a construct of human perception. This leads to profound philosophical and even existential questions about our place in the cosmos. Some physicists suggest that hidden variables might explain this phenomenon. These would be unknown factors that determine the outcomes of quantum processes in a deterministic way. However, experiments inspired by Bell's theorem have largely ruled out local hidden variables, meaning that if such variables exist, they must operate in a non-local way. This pushes us into even stranger territory, where the rules of the universe seem fundamentally different from anything we experience in our macroscopic world. To make matters even more perplexing, quantum entanglement isn't just limited to pairs of particles. Scientists have observed multi-particle entanglement, where three or more particles become linked in ways that defy classical explanation. This has led to the concept of quantum networks, which could revolutionize technology by enabling secure communication, distributed computing, and even quantum versions of the Internet. These advancements have practical implications, but they also raise deeper questions. If we can entangle particles across vast distances, does this mean we could one day manipulate quantum systems on a cosmic scale? Could we use entanglement to gather information from distant parts of the universe or even communicate across galaxies? While these ideas remain speculative, they underscore the boundless potential of quantum mechanics to reshape our understanding of what is possible. One of the most intriguing aspects of quantum entanglement is its potential connection to other mysteries of physics. For example, some researchers have speculated that entanglement might play a role in the structure of black holes. According to certain theories, the interiors of black holes could be, holographically, encoded on their event horizons, with entanglement serving as the mechanism that links these seemingly disparate realms. This idea ties into the concept of spacetime as an emergent phenomenon, where entanglement might not just occur within spacetime but actually give rise to it. Another fascinating connection is the role of entanglement in the early universe. During the Big Bang, the universe was an incredibly hot, dense, and quantum mechanically entangled state. As it expanded and cooled, the entanglement between particles persisted, shaping the large-scale structure of the cosmos. Some scientists believe that studying this primordial entanglement could help us understand the nature of dark matter and dark energy, two of the most elusive components of the universe. Entanglement also invites us to reconsider the arrow of time. In classical physics, time moves in one direction, from past to future. But on a quantum level, processes can often occur in either direction. This symmetry is broken when we observe quantum systems, creating the appearance of a forward-moving arrow of time. Some theorists propose that entanglement might hold the key to understanding why time flows the way it does, linking the microscopic world of quantum mechanics to the macroscopic world of everyday experience. As we delve deeper into these questions, it becomes clear that entanglement is not just a scientific puzzle, it is a profound window into the nature of existence. It challenges us to think beyond our everyday experiences and embrace the strangeness of a universe that is far more interconnected, dynamic, and mysterious than we ever imagined. In many ways, the study of quantum entanglement is a testament to the power of human curiosity. It reminds us that the most profound discoveries often come not from solving problems but from asking questions. What is reality? What is space? What is time? These are questions that physicists, philosophers, and thinkers of all kinds have been grappling with for centuries. And while quantum entanglement doesn't provide definitive answers, it offers tantalizing clues that push us closer to understanding the universe's deepest secrets. Yet, with every answer we find, new questions emerge. This is the nature of science, an ever-expanding journey into the unknown. And perhaps that is the greatest mystery of all, the idea that no matter how much we learn, there will always be more to discover, more to explore, and more to wonder about. Quantum entanglement offers a unique lens through which we can explore some of the most profound mysteries of existence. One such mystery is the concept of non-locality, the idea that objects can influence one another instantaneously, regardless of the distance between them. Non-locality is at the heart of entanglement, and it challenges our classical notions of separateness and independence. Imagine for a moment that the universe itself is not a collection of isolated particles and objects but rather a vast, interconnected web of relationships. This is precisely what quantum mechanics suggests. The phenomenon of entanglement implies that the universe operates on a fundamentally holistic level, where the actions or states of one part can influence others, even across immense distances. This challenges the classical view of a universe governed by local interactions, where objects interact only through direct contact or signals constrained by the speed of light. The implications of this are staggering. If entanglement and non-locality are foundational aspects of reality, then the universe might be more like a living organism than a machine. This brings us to the concept of information as a fundamental building block of reality. In classical physics, information was often treated as a secondary concern, an abstract property of systems that could be exchanged, stored, or lost. But in the quantum world, information takes on a central role. Quantum entanglement demonstrates that information can exist in a state of Superposition, where it is both shared and not shared between particles, depending on how it is measured. This leads to fascinating questions about the nature of quantum information. What does it mean for information to exist in an entangled state? How does the act of measurement collapse this information into a definite state? And perhaps most intriguingly, where is this information stored? Some physicists propose that entangled particles might share a kind of hidden quantum memory that transcends space and time. Others suggest that the information resides in the fabric of space-time itself, woven into the very geometry of the universe. These ideas are not just theoretical musings. They have practical applications in the burgeoning field of quantum computing. Unlike classical computers, which process information in binary, zeros and ones, quantum computers use quantum bits, or qubits, which can exist in superposition states. This allows them to perform certain calculations exponentially faster than their classical counterparts. Entanglement plays a crucial role in this process, enabling qubits to be linked in ways that defy classical logic. As quantum computers become more advanced, they could unlock new frontiers in fields like cryptography, materials science, and artificial intelligence. This raises another intriguing possibility, that quantum entanglement might be the mechanism behind dark energy and dark matter. These mysterious entities, which together make up about 95% of the universe, remain largely unexplained. Could it be that their effects are manifestations of quantum phenomena operating on a grand scale? Some theoretical physicists speculate that entanglement could create a kind of quantum pressure, influencing the expansion of the universe and the behavior of galaxies. While these ideas are still highly speculative, they offer a tantalizing glimpse into the potential of quantum physics to solve some of cosmology's greatest puzzles. The role of consciousness in entanglement. Another deeply philosophical question surrounding quantum entanglement is its relationship to consciousness. The act of measurement in quantum mechanics, a process that collapses a particle's superposition into a definite state, remains one of the great mysteries of the field. Some interpretations, such as the Copenhagen interpretation, suggest that observation by a conscious observer is necessary for this collapse to occur. This has led to the controversial idea that consciousness itself might be fundamentally entangled with the fabric of the universe. While mainstream physics does not yet accept the notion of consciousness playing a direct role in quantum processes, it has inspired fascinating lines of inquiry. Could our minds be quantum systems, capable of entangling with the particles around us? Some researchers in the field of quantum biology are exploring whether entanglement plays a role in processes like photosynthesis, bird navigation, and even human cognition. If these connections are proven, they could revolutionize our understanding of life and consciousness. Entanglement and the multiverse. The concept of the multiverse, the idea that our universe is just one of many, is another area where quantum entanglement might hold the key to deeper understanding. In the many worlds interpretation of quantum mechanics, every possible outcome of a quantum measurement exists in a separate, parallel universe. Entanglement in this context becomes a kind of bridge between these universes, linking their fates in subtle ways. If this interpretation is correct, then entanglement could provide a mechanism for exploring these alternate realities. Though such ideas remain firmly in the realm of theory, they challenge us to expand our horizons and consider the possibility that our universe is just one piece of a much larger puzzle. Philosophical reflections on entanglement. At its core, quantum entanglement forces us to reconsider what it means to be separate and connected. It suggests that the boundaries we perceive between objects, events, and even individuals might be illusions, artifacts of our limited perspective. In a universe governed by entanglement, everything is interconnected in ways that defy logic and intuition. As we delve deeper into the mysteries of entanglement, we find ourselves confronted not only with new questions about the universe but also with profound questions about ourselves. What does it mean to be a part of an interconnected cosmos? How do our actions ripple through the quantum web of reality? And how might our understanding of entanglement shape the way we live, think, and relate to one another? The answers to these questions remain elusive, but the journey of exploration is as exciting as the destination. Quantum entanglement is a reminder that the universe is far more mysterious and wondrous than we can imagine. It invites us to embrace the unknown, to question our assumptions, and to marvel at the intricate tapestry of existence. Quantum entanglement, with its bizarre and counterintuitive implications, does not just challenge our scientific understanding of physics, but also invites a broader reconsideration of the very nature of reality. As we dive further into the depths of this phenomenon, the exploration begins to reveal a universe far stranger than we once believed, one where the seemingly separate parts of the cosmos might be intimately and invisibly connected, no matter the distance. Entanglement and the quest for a unified theory. The ongoing quest for a theory of everything, TOE, a single, all-encompassing framework that can explain all forces and particles in the universe, often circles back to the strange behavior of quantum entanglement. One of the most profound challenges in modern physics is reconciling the theories of quantum mechanics, which governs the microscopic world of particles, with the theory of general relativity, which governs the large-scale structure of the universe. At first glance, these two theories seem incompatible. Quantum mechanics operates with a fundamentally probabilistic nature, where particles can exist in multiple states at once, while general relativity describes a deterministic universe, where the paths of objects are predictable based on their mass and the curvature of spacetime. Yet both theories have been immensely successful in their respective domains. This contradiction points to a deeper reality, one that we have yet to fully uncover. Quantum entanglement could hold the key to resolving this tension. Some theorists believe that entanglement might be a crucial piece in unifying quantum mechanics with general relativity. The work of physicist Juan Meldacena and others on holographic duality suggests that the strange behaviors of quantum particles might be related to the behavior of gravity at extremely small scales. If quantum entanglement plays a role in the fabric of spacetime itself, it could lead us closer to a unified theory, blending the quantum world with the cosmic scale. Furthermore, the idea that entanglement transcends the limitations of spacetime hints at a universe that might be fundamentally more interconnected than we can yet comprehend. In this picture, space and time could emerge from a deeper, more fundamental reality, a reality governed not by locality but by non-local quantum connections that are far-reaching and instantaneous. The limits of our understanding, the role of experimentation. As mind-bending as quantum entanglement is in theory, it is only through rigorous experimentation that we can continue to probe its mysteries. Over the past few decades, scientists have made enormous strides in confirming the validity of entanglement. The experiments conducted by physicists like Alain Aspect in the 1980s, which tested the Bell inequalities, proved that quantum mechanics predicts correlations that cannot be explained by classical physics. These experiments have since been expanded, with entangled particles being separated over increasing distances to test the limits of their influence on one another. One of the most significant milestones in the study of entanglement occurred in the 2010s when researchers managed to entangle particles over hundreds of kilometers using satellites. These experiments demonstrated that entanglement is not just a laboratory curiosity but a phenomenon that can manifest across vast distances, potentially usable for communication technologies that were once thought to be science fiction. However, despite these advancements, we still have only a partial understanding of the true implications of entanglement. One of the major obstacles remains the challenge of measuring the effects of entanglement on large systems. While entanglement has been observed in small-scale systems, such as photons, electrons, and atoms, how it scales up to macroscopic objects remains uncertain. But even as we harness the power of entanglement for technological progress, we must grapple with its deeper implications. What does it mean to live in a universe where non-locality is a fundamental property? How does this affect our understanding of space, time, and causality? And could it be that entanglement holds the key to unifying the seemingly incompatible theories of quantum mechanics and general relativity? One promising avenue of exploration is the idea that spacetime itself might emerge from quantum entanglement. This radical hypothesis suggests that the geometry of the universe is not a fixed backdrop against which events unfold but rather a dynamic construct shaped by the entanglement of quantum states. In this view, spacetime is not a fundamental entity but an emergent phenomenon, arising from the underlying fabric of quantum reality. This idea is supported by research in the field of holographic theories, which propose that the universe can be described as a kind of hologram. According to these theories, all the information about a three-dimensional space can be encoded on a two-dimensional surface, much like a holographic image. Entanglement is thought to play a crucial role in this process, linking the information on the surface to the events occurring within the space it describes. The connection between entanglement and spacetime is not just theoretical, it has profound implications for our understanding of black holes. Black holes are among the most mysterious objects in the universe, and their study has revealed unexpected connections between quantum mechanics and general relativity. For instance, the information paradox, the question of what happens to information that falls into a black hole, has led some researchers to propose that entanglement might be the mechanism by which information is preserved. In this view, the entanglement between particles inside and outside the black hole ensures that information is never truly lost, even if it seems to disappear beyond the event horizon. This brings us to the concept of wormholes, which some physicists believe could be related to entanglement. According to certain theories, entangled particles might be connected by microscopic wormholes, or Einstein-Rosen bridges, that link distant regions of spacetime. While these wormholes would be far too small to traverse, they could provide a glimpse into the underlying structure of the universe and its hidden dimensions. The idea that entanglement might be linked to the geometry of spacetime raises profound questions about the nature of reality. If spacetime is emergent, then what lies beyond it? What is the substrate of the universe from which spacetime arises? And could it be that entanglement provides the key to unlocking this deeper layer of reality? As we explore these questions, it becomes clear that entanglement is not just a scientific phenomenon, it is a philosophical one. It forces us to confront the limits of our understanding and to question the assumptions that underpin our view of the world. What does it mean to say that two particles are separate, if they are fundamentally entangled? What does it mean to say that events are caused, if causality itself is a construct of spacetime? And how do we reconcile the apparent randomness of quantum mechanics with the ordered complexity of the macroscopic world? In many ways, the study of quantum entanglement is a journey into the unknown. It challenges us to think beyond our everyday experiences and to embrace the strangeness of a universe that is far more interconnected and mysterious than we ever imagined. It is a reminder that the most profound discoveries often come not from seeking answers but from asking the right questions. And perhaps that is the true mystery of entanglement, not just the phenomena it reveals but the possibilities it opens. It is a window into a universe that is both stranger and more beautiful than we can comprehend, a universe where the boundaries between past and future, here and there, and self and other begin to blur. If the universe is indeed interconnected at a fundamental level through quantum entanglement, then our understanding of reality must expand beyond traditional frameworks. Entanglement defies the classical concept of locality, where objects influence each other only through direct interaction or via intermediaries traveling through space. This phenomenon forces us to confront the possibility that distance might not be an absolute barrier in the quantum realm. Implications for communication and information transfer. One of the most tantalizing prospects of quantum entanglement is its potential application in communication. Though entanglement does not allow for faster-than-light signaling, since the information transfer depends on classical communication to interpret quantum correlations, it opens up the possibility of quantum teleportation. This is a process where the state of a particle is transferred to another particle at a distant location using entanglement. In essence, quantum teleportation allows for the transmission of quantum information, preserving its integrity across vast distances. This process, which has already been experimentally demonstrated over distances of hundreds of kilometers, could revolutionize fields like cryptography. Quantum cryptography leverages the principles of entanglement to create unbreakable encryption systems. The concept of quantum key distribution, QKD for instance, ensures that any attempt to eavesdrop on a communication will disturb the quantum states involved, alerting the parties to the intrusion. Such advancements have the potential to make our data transmission systems not only faster but also impervious to hacking. But these practical applications are only the tip of the iceberg. The deeper implications of entanglement touch on some of the most profound questions about the nature of reality. For example, if information can be preserved and transmitted through entanglement, could it also provide insights into the origins of the universe? Entanglement and the early universe. The idea that quantum entanglement might play a role in the large-scale structure of the universe is both fascinating and perplexing. During the Big Bang, the universe existed in an incredibly dense and hot state, where quantum effects dominated. It is possible that particles emerging from this primordial soup became entangled with one another. Over billions of years, as the universe expanded and cooled, these entangled states could have influenced the distribution of matter and energy, shaping the cosmic web we observe today. The cosmic microwave background (CMB), the faint afterglow of the Big Bang, provides a potential avenue for testing these ideas. Some researchers have proposed that subtle correlations in the CMB's temperature fluctuations could be evidence of entanglement on a cosmic scale. If true, this would suggest that the entire universe is woven together by threads of quantum interconnectedness, stretching across the vastness of space and time. Some theorists posit that large-scale entanglement could lead to phenomena we are only beginning to imagine. It could help explain the behavior of black holes, where quantum effects and gravity are believed to intersect in complex ways. The theory of black hole information paradox, for example, might be informed by the behavior of entanglement at the event horizon of black holes. Could information that falls into a black hole be preserved and transmitted through entanglement to the rest of the universe? Is the fate of all matter and energy in the universe somehow encoded in quantum entanglement? These are questions that may not have clear answers for some time, but they push us to reconsider everything we know about the fundamental workings of reality. Quantum gravity and the fabric of space-time. One area where quantum entanglement might play a pivotal role is in our understanding of quantum gravity, the branch of theoretical physics that seeks to describe gravity according to the principles of quantum mechanics. Currently, general relativity and quantum mechanics exist as two separate domains, with general relativity explaining the behavior of large-scale structures like planets and galaxies, and quantum mechanics explaining the microscopic world of particles and fields. Entanglement could offer a bridge between these two theories. In loop quantum gravity, for example, space-time itself is thought to be quantized, with discrete units of space and time interacting with one another in ways that are governed by quantum principles. If entanglement is a foundational property of the quantum world, it could play a central role in how space and time themselves emerge from more fundamental, non-local interactions. In this framework, entanglement could be the key to understanding how gravity operates at the quantum level, potentially leading to a new understanding of the cosmos. Furthermore, theories such as string theory and brane theory propose that the universe is not just made up of point particles but rather one-dimensional, strings, or multidimensional objects called branes. These theoretical constructs exist in higher dimensional spaces, and their interactions may be governed by quantum entanglement. Understanding the relationship between quantum entanglement and these higher dimensional spaces could shed light on some of the universe's most profound mysteries, such as the nature of dark matter and dark energy, and the ultimate fate of the universe itself. The fabric of space-time might, in essence, be a quantum network, a web of entangled particles stretching across dimensions and scales, interwoven in a vast, interconnected tapestry that forms the very structure of the universe. If this is true, our perception of space and time as continuous, smooth entities may be an illusion. Instead, reality could be more akin to a series of quantum events and entangled states, with space and time emerging as approximations of a deeper, non-local reality. The search for a unified field and the end of locality. Quantum entanglement represents a challenge to the traditional notion of locality in physics, the idea that objects can only be influenced by their immediate surroundings. In the quantum world, however, particles can influence each other instantaneously, even if they are light years apart. This defies our classical understanding of space and time, forcing us to ask whether locality itself is a fundamental principle or merely an approximation at larger scales. Entanglement suggests that the universe might not be a collection of isolated objects interacting in separate regions of space. Instead, it could be a deeply interconnected whole, where everything is connected at a quantum level, with no true separation between objects or events. The idea of locality, central to classical physics, may be an illusion at the most fundamental level of reality. If this is true, then our search for a unified field theory, a theory that can explain all fundamental forces and particles, could ultimately involve finding a framework that eliminates the need for locality altogether. Instead of viewing the universe as a collection of separate parts, we might need to adopt a view where everything is interconnected, and where the distinctions between space, time, and objects break down. This shift would be nothing short of revolutionary. It would not only change the way we think about physics, but also force us to reconsider our place in the universe. If entanglement is the rule, not the exception, then every particle, every galaxy, and every person might be part of a grand, cosmic web of entangled existence, each one influencing the other, even across vast distances and timescales. As we continue to unravel the deep mysteries of quantum entanglement, one thing becomes clear: the universe, at its core, is far stranger and more interconnected than we could have ever imagined. Quantum entanglement does not just challenge the principles of classical physics, it invites us to rethink the very structure of reality itself, suggesting a universe where non-locality, where effects can occur instantaneously across vast distances, might be a fundamental property, rather than an anomaly. Implications for communication and technology. Quantum entanglement has already sparked immense interest in its potential applications, especially in the fields of communication and computing. The idea of using quantum entanglement for quantum communication, often referred to as quantum teleportation, has captivated both scientists and science fiction enthusiasts alike. In quantum communication, two entangled particles can be used to transmit information instantaneously, regardless of the distance between them. This has the potential to create an entirely new kind of communication system, one that operates faster than the speed of light and is fundamentally secure. Any attempt to intercept or measure the quantum state of the particles would disturb the entanglement, making it possible to detect eavesdropping attempts instantly. This is known as quantum cryptography, a promising field that could revolutionize data security. The idea of using quantum entanglement to create quantum internet networks could usher in an era of ultra-fast, unhackable communication. While such technologies are still in their infancy, progress is being made. In fact, in recent years, researchers have successfully demonstrated the ability to send entangled particles across long distances using satellites. These milestones pave the way for a global quantum network that could enable secure, instantaneous transmission of information across the planet, potentially opening up new realms of communication and technological possibility. On the other hand, quantum computing could also benefit from quantum entanglement. Quantum computers, which use quantum bits or qubits, exploit the strange properties of quantum mechanics to perform calculations at speeds unimaginable with classical computers. Entanglement plays a crucial role in this process, allowing qubits to represent multiple values simultaneously through a process known as superposition. This enables quantum computers to solve complex problems much more efficiently than current computers can, potentially revolutionizing fields such as artificial intelligence, discovery, and cryptography. Yet, as promising as these technologies are, they come with their own set of challenges. Quantum systems are notoriously difficult to control and measure due to their sensitivity to external influences, a phenomenon known as quantum decoherence. Scientists are working to overcome these issues by developing more stable qubits and improving the techniques for manipulating and measuring entangled particles. Even with these hurdles, the progress in quantum technology suggests that quantum entanglement will play a significant role in the next generation of scientific advancements. Entanglement and the nature of consciousness. One of the more speculative areas where quantum entanglement is being explored is in the realm of consciousness. The famous physicist Roger Penrose has proposed that consciousness may be rooted in quantum mechanics, particularly in processes involving quantum entanglement. Penrose suggests that consciousness is not merely a result of classical computations performed by the brain, but could arise from the quantum effects that occur at the microtubule level of neural networks. The orchestrated objective reduction, (OR) theory, developed by Penrose and anesthesiologist Stuart Hameroff, posits that quantum entanglement in microtubules, structural components of cells, could be responsible for the emergence of conscious experience. According to this theory, the non-local nature of quantum entanglement might be what allows consciousness to experience a unified sense of self and to integrate information from the brain's neural processes in a way that classical physics cannot fully explain. While this theory remains highly controversial and lacks concrete experimental evidence, it raises fascinating questions about the potential connection between quantum mechanics and the fundamental nature of mind. If consciousness does indeed involve quantum processes, then understanding quantum entanglement might ultimately lead us to a deeper understanding of the very fabric of subjective experience, how the mind perceives and interacts with the world. This possibility also brings to light the much-debated question of whether consciousness itself could be a non-local phenomenon, one that is not confined to the individual brain but instead part of a larger, interconnected cosmic system. If entanglement is indeed a key to the quantum nature of consciousness, then our minds might be more closely linked to the universe at large than we have ever imagined. Cosmology and quantum entanglement, a new understanding of the universe. One of the most exciting and profoundly mind-bending possibilities raised by quantum entanglement is its potential impact on our understanding of the universe itself. If non-locality is a fundamental property of reality, then it could mean that the universe is not a vast collection of separate, isolated parts, but a deeply interconnected whole. This could have far-reaching implications for cosmology. For instance, the concept of dark matter and dark energy, which together make up about 95% of the universe, could be influenced by quantum entanglement in ways that we are just beginning to understand. Dark matter and dark energy remain elusive because they do not interact with light or other forms of electromagnetic radiation, making them difficult to detect with traditional observational tools. However, if these phenomena are connected to the quantum realm, they could be related to entangled states that exist throughout the cosmos. The idea that entanglement plays a role in the structure of the universe also connects with recent developments in the study of black holes. The holographic principle, a theory that suggests the entire universe could be described as a two-dimensional surface rather than a three-dimensional volume, is closely related to the nature of quantum entanglement. According to this principle, information about the universe, such as the positions and velocities of particles, might be encoded on the event horizon of black holes, with entanglement acting as the mechanism by which this information is transferred. These ideas challenge the conventional view of space and time as separate, continuous entities and suggest that the universe could be understood as a holographic projection, where what we perceive as space-time is a lower-dimensional projection of more fundamental quantum information. If quantum entanglement is the force that binds this information together, it could fundamentally change the way we view everything from the Big Bang to the farthest reaches of the universe. Moreover, the possibility of entanglement spanning across the cosmos might explain phenomena like quantum fluctuations in the early universe, which could have played a key role in shaping the structure of the universe as we know it. If quantum entanglement is embedded in the very fabric of space-time, then the formation of galaxies, stars, and other cosmic structures might be the result of entangled quantum states that are intertwined with the birth and evolution of the universe. Quantum entanglement and the future of science. As we stand at the precipice of a new era in our understanding of the universe, quantum entanglement serves as a reminder that the universe is much more complex and mysterious than we can imagine. What we are discovering is just the beginning. While the strange, non-local properties of entanglement may seem perplexing and even impossible to grasp, they open the door to a future where the boundaries of science and reality are continually pushed and expanded. In the coming decades, as technology improves and our understanding of quantum mechanics deepens, we may unlock secrets about the nature of existence that have long eluded us. Whether through the development of new quantum technologies or by gaining a more profound understanding of how quantum entanglement fits into the broader tapestry of the cosmos, the future of science looks extraordinarily promising. One thing is certain: quantum entanglement is not just a quirk of the subatomic world, it is a key that could open the door to understanding the universe at its most fundamental level. It challenges us to rethink the very nature of space, time, and causality, and to explore the deeper connections that bind everything together, from the smallest particles to the largest galaxies. As we continue to explore this remarkable phenomenon, the mysteries of the universe will undoubtedly unfold before us, stranger, more interconnected, and more beautiful than we could ever have imagined. Quantum entanglement's role in unraveling the deepest questions of reality has the potential to shake the very foundations of physics, cosmology, and even philosophy. But as we explore further, it's essential to recognize that we are still only scratching the surface of this strange phenomenon. The complexities of entanglement and non-locality may not just redefine our understanding of the microscopic world but could also alter the way we perceive the universe at the grandest scales. Entanglement and time, rethinking causality. One of the most profound implications of quantum entanglement lies in how it forces us to rethink the nature of time and causality. According to classical physics, the cause must always precede the effect. But quantum entanglement seems to defy this idea. When two particles become entangled, their states are interdependent regardless of the distance between them. When one particle state is measured, the state of the other particle is instantaneously determined, no matter how far apart they are. This seems to suggest that information can travel faster than the speed of light, which directly conflicts with the theory of relativity, which holds that nothing can travel faster than the speed of light. This instantaneous connection between entangled particles raises some intriguing questions about the nature of time itself. If the state of one particle can affect the state of another particle across vast distances without any time delay, it challenges our classical understanding of time as a linear sequence of events. Is time truly a continuous, one-way flow, or is it more like a network of interconnected points, where the past, present, and future might be far more intertwined than we think? Some theorists have suggested that quantum entanglement could offer a glimpse into the possibility of time travel or retrocausality, the idea that future events can influence the past. While such notions remain speculative, they provoke deep philosophical and scientific inquiry into the true nature of causality, and whether time itself could be a product of our limited perceptions, rather than an absolute feature of the universe. This complexity leads to another question. If quantum entanglement allows for instantaneous connections between distant particles, could there be more profound connections between distant events or even entire galaxies? Is the universe as interconnected as quantum theory suggests? And if so, how far does this interconnectedness reach? Entanglement and the role of the observer. To complicate matters further, quantum entanglement also ties into the famous observer effect. The idea that the act of measurement in quantum mechanics can alter the state of a quantum system. The role of the observer in quantum mechanics is deeply perplexing. In the case of entangled particles, the state of one particle is determined when the other particle is observed, and the measurement of one instantaneously affects the other, even if they are separated by light years of space. This leads us to a major philosophical question: what role does consciousness play in the universe? Is it possible that our perception or observation of quantum events could influence reality itself? The concept that the universe may be in some way observer-dependent could open up new ways of thinking about consciousness, free will, and the very fabric of reality. One of the most famous thought experiments in quantum mechanics, the double-slit experiment, demonstrates this puzzling relationship between observation and reality. When particles such as electrons are fired through a double slit and observed, they behave as if they are particles. But when they are not observed, they behave as waves, creating an interference pattern on the detector screen. This strange shift in behavior, depending on whether the particles are being observed, suggests that our mere act of observing the universe could be influencing its fundamental nature. This connection between observation and quantum behavior opens up the question of whether consciousness itself is entangled with the fabric of the universe. Could the conscious mind be intertwined with quantum processes, making it not just a passive observer of reality, but an active participant in shaping it? While these ideas remain highly speculative and controversial, they point to the possibility that quantum entanglement is more than just a peculiar physical phenomenon. It could also be a gateway to understanding the very nature of consciousness and reality itself. As we probe deeper into the quantum world, we may discover that the universe is far more entangled with our consciousness than we could ever have imagined. Entanglement in the context of the multiverse. Another exciting possibility that emerges from the study of quantum entanglement is its potential connection to the idea of the multiverse. The hypothesis that our universe may be just one of an infinite number of parallel universes that exist alongside one another, each with its own set of physical laws and properties. The theory of quantum mechanics has often been associated with the multiverse idea through the many worlds interpretation. This interpretation suggests that, when a quantum event occurs with multiple possible outcomes, each outcome happens in a separate, parallel universe. Essentially, every possible version of reality splits into its own universe, creating a multiverse of infinite possibilities. In this context, quantum entanglement takes on an even more profound meaning. If particles are entangled, and if every quantum event spawns a new universe with every possible outcome, it could suggest that the entanglement between particles is not just a connection within our universe, but a bridge between parallel universes. This means that quantum entanglement might not be a local phenomenon but rather a universal connection that spans across many worlds. The idea that quantum entanglement could link different universes is still highly speculative, but it offers tantalizing possibilities. If the many worlds interpretation holds true, entanglement might not just describe the behavior of particles within a single universe, but could be the thread that ties together the vast, infinite network of universes within the multiverse. As mind-bending as these ideas sound, they are not entirely outside the realm of theoretical physics. Many cosmologists and physicists are actively exploring how quantum mechanics and the multiverse might be intertwined, and future breakthroughs in quantum theory may provide us with the tools to explore these concepts in more detail. Entanglement and the quest for a unified theory of everything. Ultimately, quantum entanglement might be the key to understanding one of the most fundamental questions in physics: how to reconcile quantum mechanics with general relativity and the theory of gravity. While quantum mechanics excels at explaining the behavior of subatomic particles, and general relativity describes the large-scale structure of space-time, these two theories have never been successfully unified into a single, overarching theory of everything. One of the biggest obstacles in developing a unified theory is the apparent disconnect between quantum mechanics and gravity. Quantum mechanics operates on the level of particles, where the forces are incredibly small and operate according to the strange rules of quantum entanglement. On the other hand, general relativity deals with the large-scale fabric of spacetime, where gravity rules the behavior of massive objects like stars, planets, and black holes. But what if quantum entanglement is the key to bridging this divide? Some physicists suggest that the phenomenon of entanglement could provide the framework for understanding how gravity operates at the quantum level. Loop quantum gravity, a theory that attempts to combine quantum mechanics with general relativity, suggests that spacetime itself is quantized and made up of tiny, indivisible units called quanta. If this is true, entanglement could play a role in how these quanta interact with one another, potentially offering a path toward a unified theory of everything. The idea that the entire universe, from the smallest particles to the largest cosmic structures, is governed by the same quantum laws challenges our very notion of reality. It suggests that everything in the universe, from the stars in the sky to the neurons firing in our brains, might be interconnected by an intricate web of quantum entanglement. As we continue to explore the mysteries of quantum mechanics, we might one day find the elusive theory of everything that ties together the forces of the universe. And at the heart of this theory, we may discover that quantum entanglement is the key to understanding the deep, hidden connections that govern all of reality. Quantum entanglement is more than just a strange and mind-boggling phenomenon. It is a window into a deeper, more interconnected reality, one that challenges our traditional ideas about space, time, and the very nature of the universe. It is a phenomenon that could eventually explain everything from the workings of the mind to the structure of the cosmos itself. As we continue to explore quantum entanglement, we are on the verge of discovering new and profound truths about the universe. And while the road ahead may be long and filled with uncertainties, one thing is clear: the universe is far stranger and more interconnected than we could have ever imagined. The mysteries of quantum entanglement are just beginning to unfold. As science continues to push the boundaries of our understanding, we may one day uncover the full scope of its implications, redefining not just our understanding of physics, but our very place in the cosmos. As we move further into the heart of quantum mechanics and the mysteries of the universe, it's important to recognize that while quantum entanglement challenges everything we thought we knew about reality, it is merely one part of a much larger and more intricate puzzle. The true significance of entanglement could potentially reveal a unified framework for understanding the cosmos, one that ties together the very fabric of reality, from the tiniest particles to the vast expanses of space. The role of non-locality in cosmology. One of the central features of quantum entanglement is non-locality, the idea that particles can be linked in ways that defy the conventional limitations of space and time. Non-locality in quantum mechanics means that two particles can instantaneously affect each other's states, no matter how far apart they are, without any physical connection between them. This concept seems to suggest that the universe is far more interconnected than we had ever imagined. In the quantum realm, distances between particles might be irrelevant, and the concept of locality may no longer apply. This raises profound questions about the nature of the universe itself. Could it be that space and time, as we experience them, are merely human constructs that emerge from a deeper, more fundamental reality? If particles can communicate instantaneously across vast distances, might the fabric of the universe be more of a network than a collection of isolated objects? And if space-time is not the ultimate structure of the universe, what lies beyond it? To explore this idea, scientists have looked at quantum field theory and quantum gravity, which suggests that everything in the universe is a manifestation of underlying quantum fields that permeate all of space. These fields may act like a cosmic web, with every point in the universe connected to every other point by a complex, invisible network of entangled particles and fields. This raises the possibility that the apparent separations between objects and events are illusory, that all of reality is, in fact, deeply interconnected through quantum processes we can barely comprehend. What does this mean for the larger scale of the universe? If non-locality is a fundamental feature of quantum mechanics, it could imply that the universe operates in a way we have yet to fully understand. Even on cosmological scales, such as the dynamics of galaxies, the formation of stars, or the behavior of black holes, quantum entanglement and non-locality may play an essential role. For instance, phenomena like dark matter and dark energy, which remain largely unexplained, could potentially be tied to the strange quantum behavior we observe in entanglement and non-locality. In fact, some researchers have proposed that dark matter might be the manifestation of quantum entanglement at a cosmic scale, suggesting that entanglement could be responsible for the unseen forces driving the expansion of the universe. Quantum communication across space. The concept of non-locality not only challenges our understanding of physics, but also opens up possibilities for technological advancements beyond our wildest dreams. If two particles can be entangled and affect each other instantaneously across vast distances, could we one day harness this phenomenon for instantaneous communication? The idea of quantum teleportation, which is based on the principles of quantum entanglement, has already been demonstrated in laboratory settings. In this process, quantum information can be transmitted between two distant locations without physically moving the particles themselves. This raises the exciting prospect of a new kind of communication that bypasses traditional limitations imposed by the speed of light. In theory, quantum entanglement could allow for faster-than-light communication, a development that would revolutionize everything from internet networks to space exploration. However, there are still significant challenges to overcome in terms of practical implementation, as maintaining quantum coherence over large distances remains difficult with current technology. The implications of quantum communication extend beyond communication itself. If we can develop the technology to manipulate entangled particles on a cosmic scale, it could also allow us to interact with the universe in entirely new ways. Quantum networks could lead to breakthroughs in fields such as quantum computing, cryptography, and even quantum sensing, all of which rely on the ability to control entangled particles and manipulate their states in real time. However, as with all quantum phenomena, the further we delve into these possibilities, the more we realize how much there is still left to discover. The interaction between quantum entanglement and non-locality could unlock entire new realms of technological advancement that we have yet to even begin to fully explore. entanglement, and the nature of reality. One of the most profound questions that quantum entanglement poses is not just about the workings of the universe, but about the very nature of reality itself. Is the universe truly a collection of individual particles, each existing independently in space and time, or is it a single, interconnected whole, where everything is deeply entangled and interdependent? In traditional physics, objects are often treated as separate, isolated systems. But quantum mechanics seems to suggest something radically different, that particles can exist in a state of non-separation, bound together by invisible forces that transcend space and time. This non-local connection between entangled particles suggests that the universe might not be a random collection of isolated events, but a deeply unified system, with everything influencing everything else in ways we are just beginning to understand. This idea is in direct opposition to our everyday experience of the world, where we perceive objects as discrete entities. Our everyday senses tell us that things exist independently of one another, that objects are separate, and that the flow of time is linear. Yet, quantum entanglement tells a radically different story. It suggests that at the most fundamental level, everything in the universe could be linked together in a giant, interconnected web, with no true separation between one object and another. If this is true, then perhaps the very fabric of the universe is far more fluid and dynamic than we realize. What we perceive as distinct objects or events might simply be the manifestation of a deeper, more complex system of entangled particles and forces, all acting in harmony. In this view, the universe might not be a cold, mechanistic machine, but a living, breathing entity, in which everything is connected to everything else in a vast, cosmic dance. The future of quantum entanglement, beyond the known universe. As we look ahead to the future of quantum entanglement, one thing is certain: we are only beginning to scratch the surface of what this strange and mysterious phenomenon might reveal about the universe. As technology advances and our understanding of quantum mechanics deepens, we may find ourselves on the cusp of discoveries that will revolutionize our understanding of space, time, and reality itself. Some physicists speculate that quantum entanglement could even hold the key to understanding the origin of the universe itself. Could entanglement be the process by which the cosmos came into existence? Could it explain the mysterious Big Bang, the event that created our universe from a singular point of infinite density? Perhaps the universe itself is a vast web of entangled particles, and the Big Bang was not the creation of space and time but the unraveling of an already existing cosmic web. Others suggest that quantum entanglement could be the key to unlocking the mysteries of black holes and the nature of gravity. If entanglement is a fundamental feature of reality, it could offer insight into the behavior of massive objects like black holes, where the laws of quantum mechanics and general relativity seem to collide. In the future, the study of quantum entanglement may help us understand the bizarre phenomena that occur near black holes, such as spaghettification and time dilation, and may even provide clues about the ultimate fate of the universe. In fact, some physicists believe that quantum gravity, the unification of quantum mechanics and general relativity, could be achieved through a deeper understanding of entanglement. It's possible that entanglement is the key to understanding how gravity works on the quantum level and could reveal a unified theory of everything that explains both the large-scale behavior of the cosmos and the microscopic interactions of particles. As we continue to probe the mysteries of quantum entanglement, the future of our understanding of the universe looks brighter and more intriguing than ever. Whether it's uncovering the secrets of dark matter, developing faster-than-light communication, or unlocking the true nature of time and space, the implications of quantum entanglement are profound and far-reaching. The more we learn, the more we realize how little we know. And in that uncertainty lies the beauty of quantum mechanics, the tantalizing possibility that, as we peer into the heart of the universe, we are still only beginning to uncover its deepest, most astonishing truths. As we continue to explore the far-reaching implications of quantum entanglement and non-locality, it's important to understand that these phenomena are not just theoretical oddities. They could form the foundation of entirely new scientific paradigms that will shape the future of physics, technology, and even our perception of reality itself. The principles of quantum mechanics, including entanglement, challenge everything we thought we knew about how the universe functions. The world we experience is governed by classical physics, where objects are distinct and causality is linear. But when we step into the quantum realm, these familiar rules no longer apply, forcing us to rethink what is truly possible. The quantum universe, a web of connections. One of the most captivating aspects of quantum mechanics is the idea that at the most fundamental level, the universe may be interconnected in ways that are not immediately visible to us. Quantum entanglement, non-locality, and the behavior of particles challenge our classical understanding of reality by revealing that things do not exist in isolation. Instead, everything may be part of a larger entangled network, where every particle is subtly connected to every other particle, no matter the distance between them. This network-like structure of the universe hints at something deeper. It suggests that what we perceive as separate objects, events, and moments in time might be just projections of a more profound interconnected system that exists beyond the limits of space and time. This is not just a philosophical idea, it's a scientific one, deeply rooted in quantum theory. One key example of this interconnectedness is quantum entanglement itself. When two particles become entangled, their properties are no longer independent of each other, even if they are light years apart. This phenomenon defies the classical notions of space and locality. The particles act as if they are part of a single system, with changes to one particle's state affecting the other instantaneously, no matter the distance. This is particularly fascinating when you consider the implications it might have on cosmology. If everything in the universe is connected through some form of quantum entanglement, then the fabric of the cosmos could be far more intricate than we realize. Rather than existing as separate entities, galaxies, stars, planets, and even black holes might be part of a vast quantum web, a web that transcends the limitations of space and time. Understanding non-locality through black holes. Black holes are one of the most enigmatic features of the universe, and quantum entanglement might offer a clue into understanding their strange behavior. According to some theories, black holes might not only be places where gravity is so intense that nothing can escape, but they could also be linked to quantum phenomena in ways that we are just beginning to understand. One of the most puzzling aspects of black holes is the information paradox, the question of whether information that falls into a black hole is lost forever. When a particle is swallowed by a black hole, its information, such as its quantum state, appears to be lost. This contradicts the laws of quantum mechanics, which state that information cannot be destroyed. In recent years, researchers have proposed that quantum entanglement may play a role in resolving this paradox. One possibility is that the quantum entanglement of particles near a black hole could preserve information, effectively encoding it in the entanglement itself. This idea leads to the possibility that the entire universe could be a giant hologram, with every part of the cosmos encoded in quantum entanglement. Some theories suggest that the interior of black holes could be portals to other regions of space-time, or even other universes altogether. If quantum entanglement and non-locality extend across vast distances, could black holes be the key to understanding the nature of space and time on a cosmic scale? The fact that particles can be instantaneously entangled across vast distances raises intriguing possibilities about how the universe itself might be structured. Perhaps black holes are not just regions of destruction but also points of profound transformation, capable of linking distant parts of the universe in ways we don't yet understand. The puzzle of dark matter and dark energy. As we push the boundaries of our understanding of the universe, we encounter some of its greatest mysteries: dark matter and dark energy. These unseen forces are thought to account for most of the mass and energy in the universe, yet they remain largely invisible and undetectable by conventional means. But could quantum entanglement offer an answer to these cosmic enigmas? Some researchers have speculated that dark matter may be linked to quantum phenomena such as entanglement. If quantum particles are entangled across vast distances, they could create an unseen gravitational effect that we interpret as dark matter. Similarly, dark energy, thought to be responsible for the accelerated expansion of the universe, might also be related to quantum fluctuations in the vacuum of space. The mysterious nature of dark matter and dark energy has led many scientists to reconsider the possibility that the universe is not simply a collection of isolated objects, but a highly interconnected, dynamic system. The way in which quantum entanglement could potentially give rise to phenomena such as dark matter and dark energy suggests that our current understanding of the universe's structure might be only a fraction of the full picture. The limits of our understanding, the quantum gravity dilemma. Despite the advances we've made in quantum mechanics, there remains a major roadblock that has yet to be overcome: quantum gravity. Quantum mechanics and general relativity, which govern the behavior of particles and the forces of gravity, are fundamentally incompatible at the most extreme scales. General relativity describes the large-scale structure of the universe, planets, stars, galaxies, and the warping of spacetime due to massive objects, while quantum mechanics deals with the behavior of the smallest particles. At the intersection of these two realms, such as inside black holes or during the Big Bang, the laws of physics break down, and no theory currently exists that can accurately describe what happens at those extremes. The inability to merge quantum mechanics with general relativity has led to the development of many competing theories of quantum gravity. Some of these theories suggest that entanglement might play a role in bridging the gap between the microscopic world of quantum mechanics and the macroscopic world of general relativity. Loop quantum gravity, for example, proposes that spacetime itself is quantized and composed of tiny loops of entangled particles. These loops could form the fabric of the universe, explaining both quantum phenomena and gravitational forces in a unified framework. A new era of space exploration. The deeper we venture into the world of quantum mechanics, the more we realize how much potential lies within this field to revolutionize not just our understanding of the universe but also the very tools we use to explore it. One of the most exciting possibilities is the potential to harness quantum entanglement for practical purposes, such as communication, computing, and even space travel. As we begin to understand the role of quantum mechanics in shaping the structure of the cosmos, we may find new ways to use quantum entanglement for instantaneous communication over vast distances. This could have profound implications for space exploration, enabling us to send data across the cosmos in real time, bypassing the limitations imposed by the speed of light. Space missions could be conducted with a level of precision and coordination never before thought possible. Furthermore, quantum entanglement could help us unlock the mysteries of deep space. By developing quantum sensors, we might be able to detect subtle cosmic phenomena, such as gravitational waves, dark matter, and the properties of black holes, that are currently beyond our reach. These technologies could lead to unprecedented discoveries about the universe, helping us understand everything from the origins of the cosmos to the ultimate fate of stars and galaxies. The cosmic web, unraveling the mysteries of the universe. Quantum entanglement and non-locality remind us of the profound mystery of the universe. The more we learn, the more we realize that reality is not as simple as it seems. The universe may be far more complex, interconnected, and mysterious than we can possibly comprehend. Quantum mechanics, with its strange and counterintuitive principles, might hold the key to understanding the deepest secrets of the cosmos. The possibility that everything in the universe is connected through quantum entanglement suggests that the boundaries between objects, events, and even time itself are not as fixed as we once thought. The universe could be a single, unified system, with every particle, every star, and every galaxy intricately linked in a cosmic web. As we continue to explore the mysteries of quantum entanglement, we may discover that the universe is far more connected, far more strange, and far more beautiful than we ever imagined. The journey into the heart of quantum mechanics is just beginning. The discoveries we make in the coming years could change our understanding of space, time, and reality itself, opening up new frontiers of exploration and revealing a universe that is far more interconnected and profound than we ever thought possible. As we continue to delve into the vast and puzzling world of quantum entanglement and its potential role in shaping the cosmos, we uncover even more layers of mystery and possibility. It's as if we're standing on the edge of a profound shift in our understanding of not only the universe but also the very nature of reality itself. The more we peel back the layers, the more we realize that these quantum phenomena are not isolated occurrences, but instead could be woven into the very fabric of space and time. The role of quantum entanglement in cosmology. One of the most intriguing possibilities that arises from the study of quantum entanglement is its potential to reshape our understanding of the cosmos. Until now, cosmology has been based on our understanding of general relativity in classical physics, where objects in the universe are generally seen as independent of one another, each following its own path through space and time. But the discovery that particles can be entangled across vast distances challenges this view. What if the universe itself is not just a collection of separate galaxies, stars, and planets, but a singular, interconnected entity? Could it be that the cosmic web, space itself, is entangled at the quantum level? Consider, for example, the nature of dark energy and dark matter. These invisible forces make up the majority of the universe's mass energy content, but their precise nature remains unknown. Some theorists speculate that dark energy and dark matter might not be completely separate entities at all. Instead, they could be manifestations of quantum entanglement on a large scale, with distant parts of the universe interacting with one another in ways that we are only just beginning to understand. If quantum entanglement allows particles to influence one another instantaneously, might this phenomenon be contributing to the expansion of the universe or the formation of unseen structures in space? This radical idea suggests that the entire universe might be a kind of hologram, a projection of entangled quantum states that extend across vast distances. The concept of a holographic universe, where the entire universe is encoded in the interactions of quantum entanglement, could help explain the strange and unexplained phenomena we see, from black holes to the acceleration of cosmic expansion. If everything is entangled at the most fundamental level, then the idea of space as an isolated, disconnected void starts to seem less plausible. Quantum entanglement and the future of space exploration. Beyond the implications for understanding the cosmos, quantum entanglement could revolutionize the way we approach space exploration itself. Currently, the vast distances between stars and galaxies present a significant challenge for interstellar communication and travel. Even with the most advanced technologies, the speed of light remains the ultimate speed limit for sending information or spacecraft across vast cosmic distances. This means that if we were to send a message to a probe far out in the solar system, we'd have to wait years for the message to arrive and then another series of years for a response. However, quantum entanglement could offer a potential solution to this problem: instantaneous communication. Through the phenomenon of quantum entanglement, information can theoretically be transmitted instantaneously between entangled particles, no matter how far apart they are. This might allow for the development of communication technologies that are not bound by the speed of light, making interstellar communication not only feasible but also much more efficient. Imagine a future where space agencies can communicate with spacecraft across light years, receiving data from distant missions almost as quickly as it is gathered. It's a tantalizing thought, one that could radically change how we interact with and explore deep space. But this isn't just science fiction. Quantum entanglement has already been demonstrated in laboratory settings with particles on a very small scale. The challenge, of course, will be scaling this phenomenon to practical, real-world applications. However, as quantum computing and other technologies continue to evolve, it's not far-fetched to think that we might one day be able to harness the power of quantum entanglement for instantaneous interstellar communication. Entanglement and the nature of time. Another mind-bending implication of quantum entanglement is its potential to alter our understanding of time itself. In classical physics, time is a linear progression, moving from past to present to future. But in the quantum world, time is far from linear. The concept of non-locality, the idea that events in one location can be instantaneously correlated with events in another location, suggests that time might not be as absolute and fixed as we once believed. Quantum entanglement challenges the very notion of causality, which states that cause precedes effect. In the quantum realm, entangled particles can influence each other instantaneously, no matter the distance between them. This raises the possibility that the events of the past, present, and future may not be as distinct as we once thought. If entangled particles can transcend the boundaries of space and time, might this imply that the past, present, and future are not as separate as they appear? Some theories in quantum mechanics suggest that the universe might be more like a block of spacetime, with all events existing simultaneously. This is known as the block universe theory, and it proposes that the past, present, and future are fixed and unchanging. According to this view, quantum entanglement could be the key to understanding how different points in time might be connected, even though we perceive them as separate. If everything is entangled at the quantum level, could it be that our perception of time is merely an illusion? This concept challenges our most basic intuitions about the flow of time. If time is indeed nonlinear at the quantum level, it raises profound questions about free will and our place in the universe. Are we simply moving along a preordained path, governed by the laws of quantum physics? Or do we have some degree of agency in how events unfold? While these questions may not have definitive answers yet, the idea that time itself could be influenced by quantum entanglement opens up new avenues for exploring the nature of reality. Quantum computing, a revolution in our understanding of the cosmos. The potential applications of quantum entanglement extend far beyond just communication and time. Quantum computing, which leverages the principles of quantum mechanics, promises to revolutionize our ability to solve complex problems. Unlike classical computers, which process information in binary code, using bits, quantum computers use qubits, which can exist in multiple states simultaneously, thanks to quantum superposition. When combined with quantum entanglement, qubits can become entangled, allowing quantum computers to perform calculations far more efficiently than classical computers. But how does this relate to our understanding of the universe? The power of quantum computing lies in its ability to simulate quantum systems, which are inherently complex and difficult to model with classical computers. By harnessing quantum entanglement, quantum computers could potentially simulate the behavior of entangled particles and predict how these particles interact on a cosmic scale. This could allow scientists to model everything from the behavior of black holes to the dynamics of dark matter and dark energy. As quantum computers become more advanced, they may help us unlock the deepest secrets of the universe. For example, we could use them to better understand the behavior of quantum fields that permeate space and time. These fields could provide crucial insights into the fundamental forces that govern the universe, from gravity to electromagnetism. Quantum computers could even help us simulate the early moments of the Big Bang, providing clues about the origins of the universe itself. The implications of quantum computing are vast, and the technology is still in its infancy. But as researchers continue to make progress in this field, it's possible that we will unlock new ways of understanding the universe, ways that were once beyond our comprehension. What does the future hold? As we continue to probe the mysteries of quantum entanglement, non-locality, and their implications for our understanding of the cosmos, one thing is clear: we are just scratching the surface. The quantum world is a strange, complex place, where the rules of classical physics no longer apply. It's a world where particles can exist in multiple states at once, where information can travel faster than light, and where the very fabric of space and time is woven together by entangled particles. The discoveries we make in the coming years will likely reshape our understanding of reality in ways we can't yet imagine. Quantum mechanics has already revolutionized the way we think about the universe, and as we continue to explore its depths, we may find that the universe itself is far more interconnected, mysterious, and awe-inspiring than we ever thought possible. One thing is certain: quantum entanglement and the non-locality it implies are not just theoretical oddities. They are a key part of the universe's hidden language, a language that holds the key to understanding the most fundamental aspects of existence. As we unlock the secrets of this strange and mysterious world, we may just discover that the universe is far more connected and more wondrous than we ever dreamed. As we continue to explore the tantalizing mysteries of quantum entanglement and non-locality, we inevitably encounter new questions, each more profound than the last. Every new insight into the quantum realm pushes us further from our classical understanding of space, time, and reality. The notion that particles separated by vast distances can instantaneously influence each other without any apparent connection has forced physicists to confront the limits of human intuition. To the classical mind, this idea seems impossible. How can information travel faster than the speed of light? How can particles communicate instantaneously across unimaginable distances? These questions challenge not only our understanding of physics, but also our very perception of the universe. The many worlds interpretation and quantum entanglement. In addition to the standard interpretations of quantum mechanics, one of the most fascinating and controversial theories to arise is the many worlds interpretation, MWI. This interpretation, first proposed by physicist Hugh Everett in 1957, suggests that the universe is far more complex than we can possibly imagine. According to MWI, every time a quantum event occurs, such as the measurement of a particle's position or state, the universe splits into multiple branches, each representing a different outcome of the event. This means that all possible outcomes of a quantum event exist simultaneously in parallel universes, with each universe following a different timeline. But how does this relate to quantum entanglement? In the many worlds framework, when two particles become entangled, their states remain correlated across multiple possible outcomes. If you measure one particle, the result could seem random, but in another branch of the universe, the opposite result might occur. This implies that entangled particles don't just share information in the conventional sense. They may be part of a broader web of parallel universes, where the information from one reality could affect the outcome of another. This interpretation offers an intriguing perspective on the phenomenon of quantum non-locality. Rather than instantaneously transmitting information between distant particles, the act of measurement could be revealing a deeper connection between parallel universes. Each universe in the many worlds framework could represent a different version of reality, and quantum entanglement might be the bridge between these realities, offering a glimpse into alternate timelines and dimensions. While the many worlds interpretation remains highly speculative, it provides a novel way of thinking about quantum entanglement that goes beyond the limits of classical physics. Entanglement and the future of quantum gravity. The quest for a theory of quantum gravity, a unified framework that combines quantum mechanics and general relativity, has been one of the most significant challenges in modern physics. For decades, scientists have struggled to reconcile the quantum world of the very small with the relativistic world of the very large, where the force of gravity dominates. The discovery of quantum entanglement has raised the possibility that this elusive theory might not be as far away as we think. One promising avenue is the study of holographic principles and string theory. These theories suggest that the universe may be fundamentally made up of one-dimensional strings or higher-dimensional objects that vibrate at different frequencies. In these models, entanglement could be a fundamental property of space-time itself, offering a way to bridge the gap between quantum mechanics and general relativity. Researchers are exploring the possibility that the phenomenon of quantum entanglement could offer a way to understand the nature of gravity at the quantum level. If entangled particles are connected by some sort of invisible string or higher dimensional framework, it could provide a model for the force of gravity in the quantum realm. This idea is still in its infancy, but it represents one of the most exciting frontiers in physics. One fascinating theory in this domain is the ER equals EPR conjecture, which proposes that quantum entanglement, represented by the EPR paradox, and wormholes, represented by Einstein-Rosen bridges, or ER bridges, are somehow related. According to this conjecture, a wormhole, essentially a shortcut through space-time, could be viewed as a manifestation of quantum entanglement. If this idea holds, it would suggest that the universe is interconnected not only by quantum fields but also by deeper structures, such as wormholes, that we have yet to fully understand. Quantum entanglement, in this case, could be the key to unlocking the mysteries of gravity, space-time, and the structure of the universe itself. Entanglement and the fundamental nature of reality. As we continue to push the boundaries of quantum theory, we are forced to confront the most profound questions about the nature of reality itself. What does it mean for the universe to be entangled? If entanglement connects all things, does it imply that everything is, in some sense, part of a single, unified system? The very idea of quantum entanglement challenges our perception of separateness and individuality. In the classical view, objects in the universe exist as independent entities, each with its own properties and behavior. However, quantum mechanics tells us that at the most fundamental level, everything is interconnected, and that boundaries between particles, objects, and even space itself are not as absolute as we once believed. This realization leads us to a startling possibility. The universe may not be made up of discrete, separate particles and objects at all. Instead, it might be more akin to a vast, holistic web, where all points of space-time are connected by entanglement and quantum forces. If this is true, the distinction between objects and space begins to break down, and we are left to ponder whether the universe itself is a single, unified entity, constantly shifting and evolving at the quantum level. The limits of human perception. As we reach the edges of our understanding of quantum entanglement and non-locality, we encounter a fundamental limitation of human perception. Our minds are attuned to the classical world of large objects and slow-moving processes, where things are clearly defined and predictable. But the quantum world operates on a completely different scale, one that defies our everyday intuitions. In the quantum realm, particles can exist in multiple states at once, can influence each other instantaneously, and can be entangled across vast distances, all of which seem counterintuitive to our everyday experience of reality. This raises the question, how much of the universe can we truly comprehend? Are there limits to human perception that prevent us from fully grasping the quantum nature of reality? While we may continue to make remarkable progress in our understanding of quantum mechanics, it is possible that the full implications of these phenomena will always remain just beyond our grasp, hidden from us by the limits of human cognition. At the same time, the exploration of quantum entanglement challenges us to expand our minds and rethink our assumptions about the universe. It forces us to confront the possibility that the universe is far stranger and more complex than we could ever have imagined, and that the ultimate truths of reality may lie beyond the boundaries of our current understanding. The unfolding journey. The study of quantum entanglement and non-locality is far from over. In fact, we are only at the beginning of what promises to be one of the most exciting and transformative periods in the history of science. As our tools and techniques improve, and as we develop new ways of thinking about quantum mechanics, we are likely to uncover even more astonishing insights into the nature of reality. Each discovery opens up new avenues for exploration, revealing a deeper, more intricate web of connections that bind the universe together. Whether we are investigating the mysterious behavior of black holes, the strange properties of dark matter, or the fundamental nature of space-time itself, quantum entanglement is likely to play a key role in shaping our understanding of the cosmos for years to come. The universe is, quite possibly, much more interconnected and mysterious than we ever thought. And as we continue to unlock the secrets of quantum entanglement, we may one day discover that the greatest mystery of all is not what exists out there in the vast expanse of space, but what lies hidden within the very fabric of reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.